Hello class, this is Mr. Hart. In this video we want to talk about two things. First of all, we're going to talk about volume, how loud a sound can be, which is often called sound intensity in physics. And then the second thing we want to talk about is resonance. And we'll find that these can be connected to each other in a lot of ways. But let's dive right into it. So first of all, let me ask you this question. What is volume? So if I ask you to turn up the volume on a speaker, what are you actually doing? And if you think about it, a sound wave is dependent on the hearer, right? If you scream really loud, it might be really loud to someone really close to you, but to someone that's really far away, they may not even be able to hear it if they're distant enough. So the volume, even though you can control a knob on your speaker or on your TV, is kind of dependent on who is listening and how far away they are from the system that's making the noise. And so, not surprisingly, if you think about sound, it's a wave, and it has energy associated with it, and so it's going to behave according to the inverse square law. Okay, our favorite friend, the inverse square law. So if you think about it, as a sound is emitted from a source, it spreads out as a sphere, and as the circle shown in this diagram. And so the intensity of the sound that you're going to hear is going to decrease by the square of the distance, just like the force of gravity did, just like the intensity of light did. These are all dependent on spreading out like spheres, and so they go down with the surface area, which is a square relationship. This is another way you can visualize this that I found very useful. Okay, if you think about a source emitting a sound, it doesn't even have to really be a sphere per se. If you think of sound coming out of the speaker, you could represent how much area it has to cover in this square. But if you go twice as far, that sound is now spread out twice as much in each direction. And so now you have 4 squares, the same amount of area that you have to cover, but you still have the same intensity of sound, or the same energy of the sound. And so your intensity, your volume, goes down by this square relationship. So I thought this was a really good visual for understanding this. So we know it obeys the inverse square law, but how do we actually calculate it? Well, this is how we do it. So this is our intensity equation. And again, you can think of intensity as volume, but it essentially says this. If I have the intensity of sound that I want to compute, okay, I have to know the power output of the sound. Okay, and we'll talk about what that's measured in a second. But you can think of your speakers or your voice, whatever it may be, having a certain amount of energy it's giving out every second. And then you simply divide that by the surface area of a sphere, where r is the radius, but meaning basically, in other words, the distance to you or to the person hearing the sound. Okay? So we simply take out how much power input is given into the system, and we divide it by the sphere of area it'd have to cover based on your distance away from that sound. Okay? So what are the units of intensity then? If you think about power, we've seen this before. We know that power is measured in watts, and pi and 4 don't have any units, and radius is measured in meters. So this is going to be power over the area, which is watts per meter squared. Okay, so power output over the square meter area that has to cover. So it's kind of a weird unit, but that's how we measure volume, or intensity, is watts per meter squared. So let's do just a quick sample problem. So a speaker can create a wave that has a power of 100 watts. If you stood 4 meters away from the speaker, what would the intensity of the wave be? So we know in this case that the power is 100 watts. We know that R is 4 meters. And so we just say that the intensity is equal to power over 4 pi r squared equals 100 watts over 4 times pi times 4 squared, 4 meters squared. Let's throw that into our calculator. 100 divided by 4 times pi times 4 squared. Make sure the whole bottom is in parentheses. And you should get, when all is said and done, that the intensity in this case is 0.497 watts per meter squared. Okay? Now that's all great and dandy, but what does that mean? If I told you that the intensity of the sound I'm hearing is 0.497 watts per meter squared, how do you relate that to any sound? How do you know if that's loud or soft? And so this is not a very intuitive unit, which is why you've probably heard of the other unit that we use, which is decibels. So decibel is a different scale, which basically puts the intensities on a logarithmic scale. So if I add 10 to the decibel scale, it's essentially timesing my intensity by 10. And the decibel scale has a 0 marking at the threshold of hearing. So 0 decibels would be something that you can not hear or even barely hear. And then jumping up by 10 each time is actually multiplying by 10 in intensity. Okay? So you'll notice here, we'll get to this in a second, but the threshold of hearing is actually really, really soft, right? It's 1 times 10 to the negative 12 watts per meter squared. So if I jump up by 10, you start to get the rustling of leaves. If you jump up by 2 factors of 10 or multiply by 100, you start to get to whispers, mosquito buzzings, normal conversations around 50 decibel. That's a good one to remember. 50 decibels kind of just the average ambient sound or ambient sound that you would hear as you go about your day. Then you have vacuum, busy traffic, subways. Okay, a rock concert, which is what we call the threshold of pain. Once you get past 120, that's when you start to lose your hearing because the sound is so intense. And then you get to machine guns and you get to nearby jet airplanes. I actually did research on jet airplanes. We'll talk about this in a second as well. But you're starting to get to 1,000 watts per meter squared. So the moral of the story is once you get to about 1 watt per meter squared or 120 decibels, that's when you're starting to really hear intense sounds that can cause some damage. So you want something much lower than that in intensity in terms of how loud something can be. So how do you calculate decibels then? Well, the easy way to think about it is if you know a certain amount of decibels, then you can just multiply by 10 in the intensity and add by 10 to the decibels. But the official calculation looks like this. So our intensity in decibels, okay, so this beta is what we use to represent decibels. So our intensity in decibel is 10 times the log of I, which is your intensity in watts per meter squared, over the threshold of hearing intensity, right? This was 1 times 10 to the negative 12 watts per meter squared. Okay, so this is the threshold of hearing intensity, which is really, really small. And so basically, if you get larger than the threshold of hearing, you start to get positive decibels. Now, if you haven't taken a math class where you've learned where log comes from or what it means, basically think of it as the opposite of an exponent. But for now, you just need to be able to throw it into your calculator if you've never used it before. So just type the log button, and you throw an I over 0. Make sure it's the regular log, or log base 10, not the natural log, which is often written with an ln like that. Okay. But if you throw that in, it should tell you how many decibels you have. So let's give it a shot. So, same problem. The speaker creates a wave that has a power of 100 watts. If you stood 4 meters away from the speaker, what would the intensity of the wave be in decibels? Well, last time we found that I is, 0.497, I believe, is what we said, watts per meter squared. So now we say, well, the decibels in this case is 10 times the log of I over IO, which in this case is 10 times the log of 0.497 watts per meter squared over 1 times 10 to the negative 12 watts per meter squared, which gives us, when we plug everything in, 10 times the log of 0.497 divided by 10 to the negative 12th. And you should get that this is actually pretty loud. This is 100 and basically 17 decibels. And we often write like this, kind of dB for decibels. Okay? Now notice it's kind of like radians. It doesn't really have any true units because these units would cancel out, but we kind of know how we set up this ratio, and so we often assign it these units arbitrarily. Okay? But there you go. That's 117 decibels. Let's do one more just to practice. So I worked on a research project in college working with jet noise, and this is actually another one of the videos you can do at the end of your topics if you're interested. And we were measuring the sound intensity around these aircraft because they were making sure that their personnel, the government was making sure the personnel that worked on the aircraft weren't experiencing hearing loss or trying to mitigate that because there were a lot of problems they were reporting. Anyways, some of the most intense sounds that you measure are actually around 1,000 watts per meter squared. But if you're still in the right spots, we found that you can kind of minimize that by up to 100 times. So what is the decibel range you could hear in your jet aircraft? Okay. So first of all, we need to find for this intensity what the decibel is. Okay. So if that's our I, okay, then again our decibels will be 10 times log of 1,000. I'm just going to not write the units for sake of space, over 10 to the negative 12. And that will give us, and so that tells us the most intense parts of the jet where you're standing, you're hearing sounds of approximately 150 decibels. Okay? And that's really intense. By the way, I think I wrote it should be kind of this beta, capital B, not lowercase b. Okay, but 150 decibels is really intense. So what's the range if you can get up to 100 times softer? Well, nice thing that we know is if you just minus 10 and minus 10 again, right? Minus 10 would be 10 times softer. Minus another 10 would be 100 times softer. So the full range is 150 decibels to 130 decibels. Okay? And again, we don't even have to calculate that again because we can just minus 10 to get to 100 times softer. So anywhere between 150 and 130 decibels is the intensity of the jet noise. And you can actually account for 130 decibels with head protection and stuff, but if you're at 150, you start to have some other problems. And so that was what the military was interested in. All right, let's talk about some applications of this. So one such application that I like to show is actually how you hear inside your ears. Now, if you look inside your ears or look at a diagram, you'll see that there's these little hair-looking like objects that are in a bunch of fluid. And these hairs actually connect to the brain, and they're what sends the signal. And so when you think about hearing, your little hair pieces, okay, I can't remember the scientific term, okay, but the little hair that's inside the fluid, what happens is as your eardrum is moving back and forth, these hair pieces will move as the fluid moves with them. And so that movement can actually send a signal to your brain. And so if it's a certain sound, as the sound goes back and forth, it can send the signal to your brain and let you know what the sound you're hearing is and how intense it is. It's also a good way to show what happens with hearing loss because these hairs are like these pipe cleaners. If you go too aggressively, eventually you start to deform them. And the more you deform them, right, the less they can respond to the signal. At some point you might get a total bend in them and then they're not moving too much with the movement of the fluid. Okay, so you don't want them to look like this. You want them to be nice and straight as much as possible. So the more the fluid moves, if you have too intensive sound, you can actually cause hearing loss by bending those pieces of your ear. Okay? Another great question to ask is, what are the best types of headphones? I have a lot of students that ask me this and are curious about this. Is it over the ear? Is it inside the ear? Is it the ones that kind of sit in the ear but sit a little bit farther away? Apple has the new AirPods that kind of sit more directly in your ear. And so what types of headphones are best? Well, the real answer is it's the one that requires the least intense of sound going into your ear. And so a lot of students fear that these ones that go straight into your ear can be really dangerous. And the answer is they could be, but they're actually probably safer than these ones because if this is really close to your ear, you probably don't have to play the sound really loud because you isolate the rest of the sound really well. Whereas these ones that just kind of sit in your ear, you're probably playing the sound really loud to cancel out other sounds you're hearing outside. And so it's just a combination of how well does it isolate the sound from outside so that you don't need to play it as loud. So I would say that these ones are actually some of the most dangerous types of headphones. The ones that go in your ears can be safer if you're not playing sounds as loud. And then the ones that actually cover your ears and isolate the sound entirely is obviously the safest one, because then you don't have to play the sound very loud at all because you're covering and removing the other sounds from the outside. And so it just depends. The better the isolation, better the headphone generally for your ears. All right. Let's talk about one more topic, and that is resonance. So what is resonance? Well, you may have heard the old fable about the lady that sings at the top of her lungs and she starts to break glass windows and things like that. Well, that's actually a myth based on this principle. Turns out that if you can say a sound or sing a certain tone, and you can match the exact shape and structure of an object that it wants to move back and forth at, you can cause the object to break. Think of like pushing a kid on a swing. If you push them just at the right time, they'll go higher and higher and higher, right? It's the same thing with materials. If you take a material and you push it at just the right times, it will start to move back and forth more and more and more until it can't handle it anymore. So I highly recommend looking up this video where they actually match the resonance frequency of this glass and it breaks. You can actually see this in other ways as well. There's a famous video of the Tacoma Bridge actually breaking, which I highly recommend going and watching. And what happened is that they had the wind blowing really strong in Washington, where this bridge is located, and it just happened to match the frequency of the entire bridge. And so the whole bridge was moving up and down and up and down. And it's kind of fun to watch because you can see this behavior, this shaking, this movement of the bridge until it just collapses, which is crazy because it's made of concrete and steel, but the whole bridge is shifting because of the resonance of the bridge. Now we have precautions nowadays to prevent things like this happening in the future, but it's all because of resonance. If you can move a sound back and forth at the same time that object wants to move back and forth, you can match those and cause this great movement to occur. So resonance is really cool. Let me try and show you one more demo in what's called a mechanical wave driver. And what this does is it makes resonant frequencies on these plates. And the cool thing is we can just pour some sand on this plate here. And as we play different sounds or move the plate up and down in certain ways, you can see the different resonant frequencies that occur on this plate. So this is just fun to watch. It's just a really cool demo to see that there's certain areas that like to move more and there's certain areas that like to move less. And the sand likes to gather in those areas that move less. Well, there you go. I hope this has been interesting, and thank you for watching.